Hi guys, how you doing? Assalamu alaikum. Today I'm going to be talking about the deflection of frames using the virtual work method. There's nothing new as far as derivation goes, it's the same method, but instead of dealing with a beam, we are going to deal with the frame. So let's start off with an example. For this frame below, I want you to find using virtual work theta b here, and I want you to find the horizontal deflection at C, which I usually refer to as delta C H. If I want the vertical deflection, then I will call this delta C V. So for that, I need to come up with the system of virtual frames. I'm going to call virtual frame 1 M1 for the horizontal deflection. So here I'm assuming 1 kilonewton to the right. As I said before, if we want to assume it to the left, meaning this way, then there's no problem. If you get a positive answer, then the direction that you chose is correct. If you got a negative answer, then the direction that you chose is in the opposite direction. As far as theta b goes, I'm going to choose virtual frame 2, or what I call M2, and here I chose theta to be in the clockwise direction. Okay, it's just an assumption of mine. So let's first start off by finding the reactions. Here we can take the summation of moment at A equal to 0. Then let's say we take this as the positive direction. Then 80 is going to be counterclockwise, so that's going to be minus 80 times 3, right, plus, this is going to be like that, plus 30 times 4 square over 2. Well, I'm sorry about that. It isn't 80. It's supposed to be CY, and from it, CY is going to be 80 kilo in Newton. Then do summation of Fy equal to 0 will give you Ay to be minus 80, or in the opposite direction. Summation of Fx equal to 0 will give you Ax to be 120 kilo in Newton. So that's the reactions for the real frame. Again, here's the real system. This is the virtual V1, and this is the virtual 2. Okay. Again, summation of Fx here is equal to 0. You will find Ax is equal to 1 kilonewton. This is going to create a couple for me. Then the opposite couple would be 4/3 kilonewton to counteract that moment by the horizontal force. Same thing goes over here as well. Here I have a moment, so I need to couple to just a moment, which is about 1/3 kilonewton. Again, if that's not clear to you, just take the moment about point A sub 0, and you will figure out what CY is going to be. Again, I'm not going to spend too much time on the reaction. Well, actually I did, but now let's go to the fun part, which is finding the moment functions. Here, as you can see, I only have two members, AB and BC. The obvious origins for AB would probably be A, because I don't want to mess with the joint at B. And for section BC, I'm going to use my origin at C for the same reason. I do not want to mess with the joint at B. And adding to the fact that it's a lot easier starting with C, because this is just simply this reaction times X, if I chose X to be like that, and the same thing goes over here and over here. Okay, so preparing the table, section AB, origins at A, limits is from 0 to 4, MEI is the 120x. Again, I'm going this as my positive direction, minus So again, it is 120x minus 30 times x over 2, and you get the 120x minus 15x squared. Here, because I only have 1 kilonewton, so this is just simply x, and again, this is in the same positive direction as this one. Since here there's no horizontal force, no applied moment, then the moment for this virtual frame is going to be 0. Going now to section CB, origin at C, the limits from 0 to 3. This is just simply 80x. This is 4 3x, and then this is 1 3x. All again, like I said, you have to choose the same positive sense. Then I'm going to carry out the integration. 1 over I 0 to 420x minus 15x squared x dx, and from 0 to 3, 80x 4/3 x dx, and the value is 2560 x. And theta b is just the integration, since this is 0, so there is no influence of part AB, so we're only going to carry out the integration for the part CB, and I'm getting 240, so I got two positive values, which means the direction that I chose for the sense was correct, meaning the horizontal deflection is going to be that way, and also meaning that theta b is going to be clockwise. Okay. Now there is another technique. So now going back to the other technique that I mentioned of that we used for the beams, that's we can draw the moment diagram for the beams and then use the area for the moment times the centroid. So I'm going to use the same technique here. Again, this is optional. You do not have to do if you want it, but if you feel comfortable with it in the future, just go ahead. So to draw the diagram, the moment diagram, as you remember, we had the 120 kilonewton, and here we had the distributed force. So I'm going to take the moment summation of moment at B, and that would be simply 120 times 4 minus 30 times 4 squared over 2, and then you're going to get 240 kilonewton meters. And since it's positive, so it's going to be in the positive direction, so this is actually going to be inward like this. Then I'm going to use the dotted line. Then at the middle, from here, I'm going to go WL squared over 8, which is 30 times 16 over 8, and that value is 60. Now this is going to be 240 divided by 2, which is 120 plus 60, so this value is going to be 180. So this is how my moment is going to look like. Since I already draw, again, since I went here 240, then I have to go here 240 as well. And then since I don't have any moment distributed load, it's going to be like that. Okay, I'm going to erase that now because I did this in a more representable way, I guess. So this is the parabola that I was talking about, and then this is the straight line. If we go to the virtual one, number 1, then this is, again, here I have 1 kilonewton times 4. So this is going to be, again, positive, so I'm going to have 4 inside, and this is going to be 4, so this is just going to straight to 0, this is going straight to 0. Again, I did that nicer. So these are the moment diagram. As you see here, just we draw the moment as I promised without taking the frame apart. Here, because I have no horizontal force, I only have the vertical force, so the moment here is obviously 0, which means that the concentrated moment at B is only carried by member BC, and since it's a positive moment, then this is going to be my moment for virtual frame 2. So now, as I said, we're going to multiply the area of the real frame times the value, corresponding value at its centroid from virtual frame number 1 or 2. Okay, now for the parabola, we know that the center or the centroid is located at 5/8 times the length 4, which will give you 2.5. So, which means at 2.5 meters at the virtual frame, I'm going to go and find this value right here, which is 2.5 kilonewton meters. Okay, so the centroid location was here. Then I jump to this one and take the moment value here, and I need to, since the frame has 2 members, let me erase that. I have to do the same thing for the triangle. So now here we know that the centroid from this point to this point is going to be 2/3 times the length 3, and that will give you 2 meters. So now here I go to the virtual system, add 2 meters, and read this value right here. Okay, and since this is a triangle, then it's going to be the ordinate divided by its length times x, which is 2, and this value here is going to be 8/3. All right, and then obviously I'm going to do the same thing for virtual for theta b. But here's 0, then I don't need to do anything over here. Okay, so this value is 0. Then again, this is going to be the same centroid, so this is going to be obviously 2. Then I have to come at this point, and the length is 1/3 times 2, and this will be the value right there. Okay, putting this again in a nicer representation form, then delta C horizontal, again 2/3 times 4 times 240 is your area, times the value 2.5, which is the value at YC, plus that's not 1/3, that's supposed to be 1/2, times 3 times 240 times 4/3 times 2, which is what we got over there. Then we get 2,560, which is the same as we got through integration. Theta b now here's again 1/2 times 3 times 240, the area times the value 2/3. I'm getting 240 over EI, so I'm getting the same value as well. Okay, so this ends this example right here. Oh, just one more caution: if you have negative moment, then you just put in the negative values. Okay, so let's say if this was minus 240, then you put 2/3 times 4 times minus 240 over EI. Okay, which means I have to put over EI here as well, and here as well, and here as well too. Okay, here's my eye. All right, moving on. I'm going to do another example. For the frame shown below, I want you to find the vertical deflection at D. So I'm going to impose the 1 kilonewton meter. Again, here I'm assuming the deflection is downward. It couldn't be. I think it's going to be downward, but it really doesn't matter. Again, so now I have to again find the reactions. If I find the reaction at the summation of Fy equal to 0, this is going to be simply 90, which is 3 times 30. Take the moment. Since the moment is going this way, I'm assuming that my moment will be like that. And it's going to be 30 times 3 times 1.5. Which I think is about 135. As far as the virtual system goes, Again, summation of fy equal to 0, so this again will be 1. This is going like that, and this is just going to be 3. Okay, and here are the reaction, the 135 kilonewton, 90, and here are the reaction of the 1 and the 3. This is in the way, this is in the way. It's kind of in the way. Okay. Again, here I'm going to use 2 sections because section CD has 0 moment, so I'm not even going to put that in. So I'm going to have section CB and section AB. Here, take the origin A, and here I'm going to take the origin at C. As you notice, for AB, here's a constant moment, 135 kilonewton meter, and here I have a constant moment of 3 kilonewton meters. Okay, so here's my table. Section AB, origin at A, limits from 0 to 4, minus 135 kilonewton, because this is again negative moment, and this is also negative moment, minus 3. If I go to CB, origin at C, length from 0 to 3 again. Again, I'm starting like this, and then this is just going to be no load here, 0 again. So this is just going to be, again, here's my distributed load. Then this is going to be my negative moment, and that's just going to be 30 times x over 2, hence minus 15x squared. For the virtual system, it's just going to be minus x, because it's going to be like that. So here's my minus x. Carry out the integration. So the vertical deflection at D is equal to 1923.75 over EI. Again, positive value indicates that I have chosen the right sense of direction. And that will end the virtual work for the frame. As you can see, it's kind of a straight forward. So you guys enjoy your day and be safe out there.